Okay, here is my brute force solution to the traveling salesman problem. All right, and what I use first, of course, and this is made in Python. And first it will run through this main. It'll go through here, and this will call the distance. We'll get the distance between the points. Because I used the points instead of using tslib because it should still behave similar. I mean, you couldn't really use the brute force with anything past 12 nodes because I had to, because this took 5 minutes to run 12 nodes, and doing how it's 5 to 10 factorial, it would have taken over, it would have been 13 times longer, so about 74 minutes. And I didn't want to wait that long because that's in order to get an answer to that. But so basically, it has the general same concept. But here, this finds the total distance between the points. And then this part here goes through every single permutation of every node that could ever, that's the n factorial part, since it has to go through every single possible node in order to give the best solution. And even when it gets the best solution, it doesn't stop. That's not how brute force works. It just goes to every single one until it gets to the end. And that is why brute force isn't really used for anything more than maybe 13 cities max. Unless you want to wait, because if you wanted to wait longer than that, if you want to do 14 nodes, you have to wait whatever 74 minutes times 14 is. Wait that much. About 14, about 3/4 of a day if you wanted for 14 nodes. But there's that, and here's the brute, and this other part having separate pieces. I guess I could have tried using the same, but they're separate. Brute force solution is here. It starts here, it creates the coordinate, and then it runs through, then it goes through all this, and then here's this is used to check the runtime of the algorithm, because in between that it is where the function is called to run the nearest neighbor search, which this is where it gets the distance between the points. There's two. I mean, I have two, but it's just I have a lot of unused code that I first had, because they're almost the same thing. Basically, the same thing as just two. I had wanted to read a tslib, but I didn't use it for the brute force, so I just didn't use it for nearest neighbor. I had these named wrong because I was being dumb. So this is not the brute force. This is the nearest neighbor. Just don't read that. And this gives the length. This is length. These two help find the nearest neighbor, which helps significantly increase the runtime of n factorial to n squared, which is why on the graph in the write-up, it's almost basically a straight bottom line, because that's just how much better it is compared to the brute force. Even if the the nearest neighbor is not always perfect. It always gives something close. It's never worse than 2.3 times. And in the write-up, it was only ever worse. It's only ever at 1.3 times worse. When it was at the worst. There was many times where it was the optimal solution, but that was only for when it was lower. The best for the higher was probably 1 or 2 off, 3 off, coming from like 70 weight, like 60, or 70 weight being like 72 or 75, which is pretty cool and stuff. Yeah, there's a lot of code in this, but most of it is unused. This comes from me for messing around for like a month, but almost forgetting to record because I didn't read that last part where we had to record a video. Back to looking at the brute force. Nothing else more I can say, but yeah. Oh, I should probably have it running. Oh shoot, no, hold up. 1, 2, 3, 4, 5, 6. Should take a couple seconds, right? Yeah, there we go. Yeah, see how that ran? This is only 10 nodes, so it ran in about 2.3 seconds, which is what was supposed to happen, and that's why I don't, because any higher it would take 5 minutes. It was the next one, highest one, adding 1 more node. And for the, whoops, I ran the wrong one. If I run the nearest neighbor, which is this one, it runs through each node to find the nearest neighbor to that one, and it gives a running time of how long it took to get there. And I just took the average of all those to get a better average on how long it normally takes to run through the algorithm. And this is how I got the best and worst case for these. How the optimal was about, I think, 55. And the best it seemed to run is 57. So this is only about 2 off the optimum. Oh, this just helped give if it could, which is, I don't know, just something I thought was pretty cool. It like does like it checks inside. It doesn't affect the runtime of how I calculated this, but it was just something cool I saw. I just didn't feel like getting rid of it while recording this. It does a local search, which helps try to improve the nearest neighbor, which it did pretty cool. But yeah, the best was off by only 2, which was 57 compared to 55, which I believe is what, yeah. Found best solution, which was 55, and 6. Well, this, because that helps. This also doesn't affect this time. This which just helped me calculate, so I know. I mean, I guess I also ran in here, so I knew what the best was too. I guess I also ran it in the brute force, which gave me the time for the brute force. 59.76 seems to be the worst, which is pretty bad compared to 55. It's like 1.5 times worse. But that's funny how those are random. It's like twice as worse because it's random. But yeah, that's the code. Bye.